band restricted tubes. And for example, for the same quantity of product, in the application lab in Karlsruhe, they have tested the difference in signal to noise, and they have found that with the capillary, they have a better signal to noise than with the restricted tube. Next slide. So some results obtained with this 3mm cryoprobe. Next. So this is 1 microgram tryptophan in an active volume of one in the active volume. So this is actually the total quantity of sample inside the capillary is 1.2 microgram, but there is only 1 microgram that is in the active volume. And this is the signal to noise observed with the different capillaries. You see that the smaller capillary you have, the better signal to noise you have because you have less solvent. Next slide. This is a single scan COSY and TOXY in 1 microgram of tryptophan. COSY in 8 minutes. This is a COSY here, and this is the 1D. This is a TOXY here in 9 minutes. Next slide. This is now 19 micromolar solution. Okay, you see it's very nice signal to noise in 128 scans. Next slide. This is now 10 nanograms of tryptophan in 7 hours, 1.9 micromolar. I guess this is as low as you can get. Even to prepare the sample, it would be difficult. But this is what you will be able to obtain here. Next slide. Okay, next. Next. This is an inverse experiment obtained with 250 nanograms in 13 hours. Next slide. And this is carbon 13. I will go faster on that next. Okay, so in terms of sensitivity, after these explanations and all those spectra, what did I show? I showed that different solutions have been developed to enhance the sensitivity of NMR experiments significantly. And I've also showed that the choice of the solution will depend on the application. And the chance that you have here in HEG is that you will already have, because this is what we have been working on together, you will have those different technologies at your hand, and you will have to choose the right one depending on the results and the type of application that you want to get to. Next slide. And this summarizes well the picture. You see now why you have not only a better signal to noise due to the NMR spectrometer, but also here this quantum jump due to the cryoprobes. Next. However, this is all nice, but everything is not always as nice as it looks. Because if you have better sensitivity, then you have better sensitivity to your signals, but you have also a better sensitivity to external perturbations, or to perturbations external to the sample, but they might be coming from the NMR spectrometer itself, for example. And you can see here, typically you have here a spectrum recorded on a cryoprobe, and here a spectrum recorded on a standard probe. Next. What do you see? You see that if you have noise coming in, it is probably obvious for everyone that you will see the noise much better here than here. And so when we came up with this technology, with the cryoprobes, we suddenly realized things on our electronics which was creating artifacts that we never saw before. So this development in probes, following the development in magnets, pushed Bruker to develop the spectrometers, the console. And the console that you will see coming in the next months, you will see that the electronic will be slightly different from the electronic that you have in console from 2 years ago, because the electronic has to be continuously developing because of this problem. Next slide. So spectrometer, oops, please go one backwards. So spectrometer performance must be correlated to probe performance. This is obvious. And therefore the necessity for Bruker to always keep on developing the spectrometer electronic as sensitivity goes higher. Next. So I will go a little fast because I don't want to go too much in detail of electronics because you are chemists. But these are different things which will affect the result on your NMR spectrum. Things which have to do all with electronic. Some of the things you can understand, for example, temperature here. If there is a temperature change in the console, then it can affect your NMR spectrum. Next. Next. No, just one thing. Just one sentence here that has to be remembered. Is that those problems, temperature, aging, interferences, we found out that they were coming more from analog circuitry than from digital circuitry. So as time went by and went on, we tried as much as possible to have our consoles, our spectrometers change and to put the more digital electronic in it and the less analog electronic. And this is how we came with the digital electronic concept, which is the concept of the advanced spectrometers. Next. Okay, these are problems that you never see on an NMR spectrum, but these are real problems that you see if you look at your pulses with an oscilloscope. This is the pulse that you would have to have an ideal pulse. This is what you use to excite the spins before you look at the result. If you start by not exciting the spins correctly, your result will be corrupted. And there are many reasons why the spins can not be excited correctly. For example, you see this is wrong. This is because the rise time is too long. This is wrong, this is because there is an overshoot. This is wrong, this is because the power is drooping after the first starting of the pulse. This is, okay, these are other effects that I don't want to go into. But all those effects are bad for your NMR spectrum. Next. Okay, I'm going to do just a little slide to show how you generate a pulse. First of all, if you do, you all know what a cozy experiment is. This is the experiment which allows you to correct proton and proton. Okay. This is something that you know. In order to get a cozy, you have to have a succession of RF pulses. So those pulses here are described. So this is a pulse, this is a pulse, this is a pulse. This is the timing of the pulse sequence. Next. Then inside of those pulse sequence, you put a frequency that you synthesize with a synthesizer. Next. This gives this result. This is a pulse with a frequency. For example, you have a pulse on the proton frequency, you have a pulse on the carbon frequency. Next. Then you modulate your pulse, depending on the experiment you want to do. Next. This gives this result. Then you multiply your pulse by different values in order to have small pulse, large pulse. Next. Next. And you scale it. And this is what comes into your NMR linear power amplifier. Next. And this is basically what the probe and your sample, this is what they are seeing. And if this probe is much more sensitive, as I just explained, then it will be much more sensitive to anything wrong here. And you see that there are many steps that can go wrong. This is one step, etc., etc. So we have to take care that all of those steps are very well taken into consideration. Next. So this is just a schematic representation of what was going on before. These are all the steps necessary to generate what I just described. You see that each of those steps, this is logical. Each time you have a new step, you can introduce an error. So the less steps you have, the less errors you will have at the end. And the better this will be. Also, each step you introduces a delay. And the more delays you have, the worse your sequence will be at the end. Next. So what we did is that for all those steps, we tried to put the maximum number of steps in one electronic board. Next. And this is what we have done. This is one print only. Before it was two prints. Next. And this is one unit only. Before it was 3 or 4 units. Including units which were bought by outside suppliers. So we were really depending to create that on outside suppliers. Now this is done completely by Brooker. And next slide. shows you, okay, this is really electronic, and this is this new unit which is going and you will receive in the new NMR spectrometers. This is called SGU. Next. By reducing the number of steps and reducing the number of boards, we have better sequences, we have better signals, we have better spectra. Also, we have much more room because we need less boards. So from this type of configuration, which you know already because you probably have something looking like that in your NMR lab, for an advanced with 2 channels, which will look like that before, it now looks like that. And in addition, there is additional space to be able to put an additional channel. So now, an advanced electronic bay with 3 channels is half of the size of an advanced that before with 2 channels only. Next. Okay, so I will skip that. This shows just that we are, just a few words. We are able now to have 2 pulses, for example, back to back, with a delay between the 2 pulses, which is nearly 0. This one with a phase 0, for example, and this one with a phase minus 180 degrees. So you are able now to have 1 pulse, one after each other, with a shift of phase from 0 to 180 degrees. And the delay, if we look at the scope, the delay is actually 76 nanoseconds between one pulse and the other pulse, whereas the specification is 300 nanoseconds. Next. In addition to that, we also have a better product for the amplifiers, and the amplifiers that you will receive will be better than the amplifiers from 3 years ago. Not that they were not good, but they have become better because we have kept on doing developments. So this is the when I say old-fashioned, this is the, let's say, 2 years or 3 years ago black 300. They were big and heavy, sensitive to temperature variation. Next, and the new ones. See, this is the slide, this is the old one, this is the new one. So it's slightly smaller. Next. But inside you can see that there is less and much more compact integrated electronic. So all that to have better performance. Next. So in conclusion, concerning this electronic evolution. So the advanced spectrometer gets better to meet new requirements of modern NMR in terms of sensitivity. The introduction of these cards is a key factor of this evolution. Performance of the consoles, I'm sorry, this was halfly translated to English, so I will do the translation online. Performance of the console have been dramatically improved, and this evolution allows to have a universal console for different type of applications for both liquid, solids, and microimaging. This is also a striking point. Next. So, do you still have 10 minutes? Or?
You're leaving tonight, so we can't. Right.
It's up to you. Okay. So, if since the beginning of my talk, what did I explain? I explained that we got higher magnets, higher sensitivity due to probes, better console because we have to. This allows to introduce NMR in a completely new world. Since many years, there was possibility to couple, and this is really interesting for chemists. For many years, there was the possibility to couple liquid chromatography and mass spectroscopy. Mass spectroscopy is, of course, much more sensitive than NMR spectroscopy. Still, after all those progresses, mass spectroscopy is more sensitive. But mass spectroscopy gives relatively limited number of information if you compare that to the number of informations that NMR will provide to you. There is no structural information in mass spectroscopy. So the strength of introducing LC coupled to NMR, which has now become an established sensitive analytical tool, you have the structural power of NMR. Of course, it's non-destructive, so you can recover the sample. Okay, the drawbacks, it's less sensitive than MS. You have to use deuterated solvents. And you need some other spectroscopic tools to identify the LC peaks. But this is okay. Next slide. So the state-of-the-art LC NMR systems go from 400 to 800 megahertz with ultra-shield magnets if possible. we have full automation. This is very important so that it can be easily used in your NMR lab. And I will speak about several things. You have stop flow and you have loop collection. This is the LC-NMR system installed in the 800 megahertz of Karlsruhe. This is, by the way, the 800 megahertz magnet actively shielded. Here is an LC-NMR probe, and this is the LC-NMR system. And you see that since this system is shielded, the LC-NMR column is closer. Next. Okay, what's the principle of LC-NMR? You know the principle of liquid chromatography. You are a chemist, you have a mixture, you put this mixture is represented here by 4 different peaks of 4 different colors. This is supposedly 4 different compounds. You have this mixture, and you put, actually, the mixture, no, please go back. Actually, you put the mixture here, and before, when it is a mixture, all the colors coming together gives a brownish color. So this is the mixture. The mixture goes to the column. This is liquid chromatography, nothing is new. And out of the column come the 4 different samples with different timing. And then what do? Then we go to the NMR. So we have one option, is to do what is called direct stop flow. So we have those 4 compounds coming outside of the LC column, and we push them in the NMR probe. And suddenly there is one compound coming in the NMR probe. We stop the whole thing. We do the NMR measurement. Of course, the faster, the better. Because if it's not fast enough, then in here there can be some peak can start to expand and to be together again. So the faster the better. But then we do the NMR and then we continue. And we go to the next. This is a method called direct stop flow. So you separate, you send to the NMR directly, and you stop it. Each time there is something in the NMR cell, you stop it. Next. And then once it's in the NMR cell, you can slice it in time. Okay, I don't want to go into those details. Next. The other solution is to store in different loop, like a sample changer. So you have a loop storage. This is the loop storage. And you can store the different fractions in the different loop compartments. Next. You see, this is a loop cartridge. And all of those capillaries here, you have 36 capillaries. You can store up to 36 fractions. And then, once you have stored those 36 fractions, you send them to the NMR. And then you have all the time. Basically, this is now a sample changer where you have 36 samples that you will be able to send to the NMR spectrometer when you want. Next. Next. So you have those 2 techniques at your disposal. You do either direct stop flow or you do peak sampling. And this is the result of the 2 techniques. This was to show that actually whether you do it with direct stop flow or with peak sampling, you don't lose anything. The signal to noise is about the same. Another issue of LC-NMR is that you do liquid chromatography. So you do liquid chromatography with an elution solvent. And usually you don't use deuterated solvent because this is extremely expensive. So you use a protonated solvent as the eluent of your liquid chromatography. And then when you are doing NMR, you have many peaks that you have to suppress. So you have to have a spectrometer which is good enough, and I have to say you also have to have an operator of the NMR system who knows how to do a solvent suppression. This is, for example, you see this is the mixture used for chromatography here in this example. Huh? You don't have to use that. This is a bad example. This is D2O, 89%, methanol, 8%, acetonitrile, 3%, and octane 1-sulfonic acid, 0.25%. And you have to, and those are the peaks corresponding to the solvent, not corresponding to your product. So that means that in order to see the product which is here, you have to suppress that. There are 7 peaks. You have to do a solvent suppression of 7 peaks simultaneously. There are techniques to do that. It's not difficult. And you will be trained how to do that when we install the LC-NMR system. Next slide. Next. I just want to show you an example. Okay, that's an example. So, I don't want to go into the chemistry of that. I just want to show you what I just want to describe again what LC-NMR is. This here is a 2D representation, as you can see. But this is not a 2D experiment. No, go back. What do we see? Here, this is the axis of chemical shift. So this is an NMR axis. But this is here the elution axis. And actually here you see a scale in ppm, here you see a scale in minutes. So this is not a 2D experiment. This is a succession of 1D experiments of the chromatographic elution as time goes by. So this is called an on-flow measurement, where the elution is going on, and as the elution is going on, every minute, for example, we do a 1D spectrum. And then we represent that with a chemical shift axis and a time axis. And what you see here is an NMR chromatograph. What you see here, this. These are all different samples taken at different moments in time with all the same experiment. This is each time a 1D spectrum. So this here, if we take a row out of that, we will get the 1D spectrum of this compound. If we take a row out of that, we will take a 1D spectrum of this compound. So this is extremely powerful because you see directly the NMR, the chromatogram, and the chromatogram, and you see it from an NMR point of view, and you know that NMR is quantitative. This is new for LC, because if you do a UV chromatogram, this is not quantitative, because you know that the response of UV depends of the number of chromophore groups that you have on your molecule. The more chromophore groups you have, the bigger UV peak you'll have, and the less chromophore groups you'll have. You might even have no peak if you have no chromophore. And it happened over the years that we had many surprises during demos because people were coming with mixtures. Okay? Here is my mixture. I want to see an LC-NMR spectrum. And they had a UV trace of their mixture. And they thought this is the main product, this is the secondary product. And it turned out by NMR that first of all, the main product was not the main product because it had just a benzene group or something like that. And actually there were many impurities that could not be seen with UV and could be seen with the NMR. Next slide. Okay, so this is just to explain that each row corresponds to a different molecule. So this was an example of ICL migration in this experiment, and okay, I don't want to go into too many details. Next. This is interesting. This is, for example, a mixture coming from a peptide synthesis. You do a peptide synthesis with a mixture of 3 peptides. Okay, you have a library of tripeptides. Sorry, and this is the LC-NMR that we have. If we do a zoom on that, again, this is not an HSQC. This looks like an HSQC, but be careful, this is not an HSQC. These are 1D spectra plotted over time. Okay, you see very well the separation here. I mean, this is a really powerful method. Next. So, for example, if you extract the row corresponding to this moment, you have here the NMR spectrum, the 1D NMR spectrum, where you directly have the 1D NMR spectrum. So then you understand that if you have a very powerful and sensitive probe, like a cryoprobe, well, not only you're able to do the 1D, but you also can do, yeah, go ahead. Yeah, go ahead. not only you can do the 1D, but you can also do the 2D, if you have enough time. But you have enough time since you have a cryoprobe, so it goes very fast. So now, you do the chromatography, and you can get out of it the 1D spectrum, the carbon spectrum, the correlation, the COSIB, the HSQC. This was an LC NMR application done, go back one step. This is the LC NMR application done on a wine concentrate, for example. And you can see how many different compounds are in it. You can basically do it on every field involved with analysis of mixture. Body fluid analysis, for example, is very important now in Europe. You can use this application. Next. Okay, so, go ahead. So, what I wanted to discuss during this talk, and I'm almost finished. We spoke about technology of magnets, we spoke about probes, we spoke about spectrometers, and we spoke about, this is a major new application, the coupling of LC to NMR. And also, it's the application that you will be able to do here, so I thought it was very important to discuss it. Next. So this was just an overview of what, this is something I showed this morning, an overview of what we have been developing over the last 5 years at Bruker. The development is taking place in different sites. There is development in France, development in Switzerland, development in the United States, and development in Germany, all coming to the same spectrometers. Next slide. And with this, I would like to finish my talk and thank you for your attention.
Alan, I want to ask very specific two things. What extra advantage you get by using ultra-shielded magnet other than space, it's just more space efficient? I mean, the ultra-shielded magnet, which is much more expensive than normal magnet, is just more space efficient. What other advantages you get out of it?
The driven force was space. Out of this development, we redesigned completely the magnet coil design. And in doing that, we obtained, if you want, we did not use the existing magnet coil on which we put a shielding coil. We had to redesign completely from scratch the whole thing. You cannot have one without the other. If you take out the shielding coil, it will be rubbish. Basically, the shielding coil helps to have a better homogeneity of the magnetic field inside the magnet. So it's a completely new design. At the beginning, we kept two product lines, non-shielded and shielded. This was in 95, 96. And at one point, the market told us, you can stop non-shielded, because nobody wanted non-shielded magnets. So if you want, the fact that we did developments helped to produce a better coil, better geometry. It's more homogeneous. The homogeneity volume is bigger. It's more insensitive also to external perturbations, because when we did this development, we had to take that into account. For example, this is easy to understand. There is space, yes, but if, for example, you go with a truck, with a trolley, in the 5-gauge line, you create tremendous perturbations on your magnet. But if the 5-gauge line is further away, then the perturbations will be much smaller. The result is that all our magnets, from 300 to 700, are all actively shielded. We dropped the production of non-shielded magnets, and therefore the cost of the shielded magnets went down, and there is no more difference. The only difference that you can find is for the very specific 800 megahertz magnet, where the difference in price, and I mean the production, we do not produce as many magnets at 800 as we do at 500, obviously. We have the capacity to produce 40 very high field magnets per year. Okay, that is 800, 900, 800 shielded, and 750 white bore. So 40 per year is not a large compared to the other type of magnets. So for the 800, the difference in price is so high that we kept the two products. But if in 5 years from now nobody buys the non-shielded 800, we will also drop it.
Okay. The second question is about the rationale of using cryoprobe. You see, when you have a small quantity of sample in macromolar concentration, nanogram of quantity, then you get sensitivity enhancement several-fold. You also see sensitivity enhancement of whatever you have in the solvent also. So do you recommend a specialized solvent for that particular technology, or even a common solvent works? Because my perception is that you would get larger signals for solvent impurities too.
This is right at the heart of the question. There are several possibilities. And again, depending on your application, you will have to choose the proper technology. If you have an insoluble or partially insoluble molecule, you can forget about small volumes. Because the smaller the volume will get, the smaller quantity of products you will get. And you will lose completely your... If you have biological products, or if you study for research reason, product in a certain physiological situation. For example, if you study a mixture of amino acids which are to be compared to a real life system, to a plant or to an organ, okay, you cannot concentrate it, because otherwise, if you concentrate it, it will give you the information that it will get will be not significant, because you will be outside of the physiological conditions in which it has a significance. So in these cases, you can forget the small volume foods.
Okay.
If on the other hand, you go to you extract product from a plant and you have a nanogram, a few nanograms or a few micrograms, which you know is highly soluble, then you have the advantage, the absolute advantage is to go to the smallest volume, because you will have less impurities. And in terms of solvents, there is no way to choose. No solvent producer has means to control the quality of the solvents as you have in NMR with a cryoprobe. So you have to pick up the solvent and you have to ask for the quality of the solvent after several trials and errors. Of course, we can help you, we can give you some recommendations, we can tell you what we use, but you will have to try. You can take solvent with such and such purity, and you see if it's sufficient for your needs. If it's sufficient for needs, that's fine. If it's not, you have to ask for to the supplier for a higher purity.
Okay, again, talk about the macroprobe. Macroprobe versus nanoprobe. The only thing which I can see as an advantage is a smaller quantity of sample, but it's not really time efficient. You require the same time which you need in, maybe sample efficient. The time is not time efficient, first of all.
It's sample efficient. It's time efficient if you have the proper sample. If you have milligrams of your sample, you don't need it. And actually, you will not even be able to put it in your 5 microliter volume, because it will be so viscous you will not be able to do anything with it.
But for instance, if you use literally a capillary, you hang your capillary in a normal NMR tube with using a non-active NMR solvent like carbon disulfide or carbon tetrachloride, you still can do the same thing, isn't it?
Yes, but you will have, in this case, you will have a much better sensitivity if you use a microprobe, because then you will have your coil much closer to the sample. You will win a lot in what we call filling factor, and the sensitivity will be tremendously higher. If you put a 1 millimeter capillary in a 5 millimeter probe, and in a 1 millimeter probe, the difference will be considerable. Not only that, also it's very difficult to shim to have a good shim with a 1 millimeter capillary in a 5 millimeter coil. It's much easier to shim a small coil, because if you have a small coil, you observe a smaller volume, and it's easier to correct inhomogeneity in a smaller volume than in a big volume.
Can I ask a question? You talked about solvent separation technique in NCNR. Can can the same technique be applied while recording normal proton or C13 NMR? Because, for example, if we have our sample solvent in methanol, sometimes the sample peaks are buried under the signals of methanol. So can this technique be applied to normal proton and C13 NMR recording? You got my question?
Yes, I heard the question, and I say yes. It's possible to apply the same solvent suppression techniques that we use in LC and MR. It's possible to apply them in standard. This is, LC and MR, from the NMR point of view, is just NMR. Okay, so the solvent suppression technique that you use is a solvent suppression technique that you use in NMR, and it's just a pulse sequence, and you can use it if it's with LC, or if it's with not LC, with standard sample.
I'm not sure whether it is being used at our place or not, so maybe perhaps you can help our people to... Yeah, using that? Yeah, using that. Okay. Thank you.
600 megahertz experiment. There, the impression of the scientists is this, that the advantage in using the 600 machine is not so much as compared to the 500 with relation to sensitivity and resolution. But the price is almost double.
Yes.
Do you have any comment about it?
Yes, I have two comments. The sensitivity improvement goes with the square root of the ratio of the field. Is the square root or is no? It's the power. It's the ratio to the power of 3.3 over 2, so 1.5. So this is what you get in sensitivity. Of course, you have also better separation of peaks. So if you have a huge proteins with 1,000 peaks one on top of each other, and if the 600 is just going from that to that, it might not be very significant. On the other hand, if you have the product on which you have two peaks that you cannot see at 500 and you can see them like that at 600, then it's very significant. So the increase in sensitivity and signal to noise and sensitivity, this is physics. The price is, the magnet is twice the amount of the 500 magnet. The magnet at 600 is twice the amount of the magnet at 500. Why is that? The reason for this, and if you go to 700 and 800, it's even. The reason for that is that the technology of the superconducting material gets more and more complicated as you go upfield. The number of filaments, for example, in one turn inside, I showed at the beginning a cut of the 800 megahertz coil filament. You have, I think, if you go from 500 to 600, you double the number of filaments. It's much more expensive just to build the magnet. The DWAR is about the same price. The technology that we use is about the same. The price of the material is much higher. And this is really the difference of price between 500 and 600, and between the 700 and the 600 comes from the magnet.
You know, the reason why we didn't really go for a higher field NMR, although we had an option of going to 800 and even 900 also, precisely the same reasons. We decided to buy 600 with crypo, which is much better than going to 700 and 800 with a normal.
This is true.
So that was an advantage.
This is true. If you look at the sites in the world which have invested in 800 and 900, these are sites which are mostly involved with biostructure analysis and protein structure determination, what we call now proteomics. For example, in Japan, there is this Recon Center where they have installed, I think we have 6 800 megahertz systems. And this is just to produce protein structures. If you are in natural products, then the interest of going to higher than 600 might not be. But of course, I can return to what Iqbal just said. If you put a cryoprobe on the 800, It will be much higher sensitivity than the cryoprobe on the 600. Because now we have the technology of cryoprobe up to 900, so of course 2 years ago this was not existing.
What time are we supposed to meet, Sharma?
2 o'clock.
2 o'clock? 2 o'clock.